I'll call this ceremonial session to order. I'm Steve Iona, Chair of the Awards Committee, and we're going to begin today with the Richtmyer Memorial Lecture Award. Floyd Richtmyer served as the 4th president of the American Association of Physics Teachers. The Richtmyer Memorial Lecture Award recognizes those who have made outstanding contributions to physics and their communication to physics educators. Richtmyer's life displayed his interest in both the contributions and their communication through his service as president of AAPT, as well as president of the Optical Society, as well as president of the American Physical Society, as well as editor of 2 journals. AAPT is pleased to present the 2015 Richtmyer Memorial Lecture Award to Derek Muller of the YouTube channel Veritasium. Let me ask you to come forward. Derek describes himself as someone who makes YouTube videos, TV shows, documentaries about science, engineering, and critical thinking. He claims to be guided by the Richard Feynman quote, the first principle that you must use is to not fool yourself, and you are the easiest person to fool. His work with Veritasium has over 200 video uploads, close to 3 million subscribers, and over 200 million video views. Muller's works have been featured in Scientific American, Wired, and Gizmodo. His work is informed by his PhD in physics education research from the University of Sydney with a thesis, Designing Effective Multimedia for Physics Education. Derek has set a high bar with his natural gift for being an on-camera and creating unique science videos that are educational, entertaining, and informative. Continually striving for relevance and comprehensibility, his productions have included videos on jetpack rocket science, precession, can we go the speed of light, where do trees get their mass, and why does the Earth spin? The high quality of his productions have been recognized as a winner of the Cyberscreen Science Film Festival. As he looks ahead, his goals include to get better at his craft, to make science more beautiful, and to encourage people who would not ordinarily be interested in science to take a more critical eye to their surroundings and to revel in the things that they can learn. Each of these is a mark of a good teacher and a good communicator. We look forward to Dr. Muller's talk about why some confusion is good evidence for how to make learners think.
Well, thank you so much. I am truly honored by this award. And more than anything, I think I'm excited just to be here speaking with you today, because the people in this room have supported me and helped me achieve what I've been able to achieve. Really, honestly, without you, it would not have been possible. So it's great for me to come back and to share with you my experience. And when I think about doing that, sharing my experience with you, I think of the wealth of experience in this room. And I feel like all I can do today is add my small piece to the vast body of knowledge which is physically embodied in you. The talk I originally called Why Some Confusion is Good, and then as I was struggling to write the talk, I realized there was something else I wanted to talk about. But it's related, I promise. It's related. Can you learn anything from a presentation? Which I think is a pretty good topic for, a presentation. So it's quite meta. Now, I was also reflecting on where I was 10 years ago. And where were all of you 10 years ago? I was, almost 10 years to the day, at the AAPT winter meeting. Do you remember where it was in 2006? It was in Anchorage, Alaska. Okay? Anchorage. That was my introduction to this community. And on my way to the conference, I saw a moose. Okay? This is legit. It's much tamer than the wildlife on Bourbon Street. But I've got to say, I like the choice of location this year, so thank you to the AAPT committee. So let me start with a question for you, a true or false question for you. Water drains, it swirls the opposite way down the drain in the southern hemisphere compared to how it does here. Who says that that is true? Water swirls the opposite way. You're going to have to participate because you guys are, you know, physics educated. Who says that's true? Who says that's false? Okay, it seems like there's some confusion there. Some confusion is good. Who abstains? Who's not answering? Smart, wise. If you guys bother me about this at the end of the talk, I'll show you the answer. I'll show you the video. Who has seen the video? Who's seen the video? Who's not seen the video about this? Okay, so that's good. We'll be educating a lot of you if we get to this point. Okay, so let me ask you another question. This is a pretty standard research question. This gets asked of thousands of incoming college students, so let me ask it of you, okay? Here's the setup. You go into a cheap store, like a dollar store, discount store, okay, and you buy a toy bat and a ball. And together, they cost $1.10. Now, if you know that the bat costs $1 more than the ball, how much does the ball cost? You can shout it out. I heard some of the right answer, which is encouraging. But what I will tell you is that when this question is asked of college undergraduates in the United States, over 80% get this question wrong. They say the answer is 10 cents. The ball costs 10 cents. Well, then the bat would cost $1.10, and together they would cost $1.20. So it obviously doesn't work. And it's not like the students are idiots, right? The students can clearly do this math. But for some reason, they don't do the math, and they put down the wrong answer. So I kind of want to store these questions away in mind as we contemplate the bigger question. Can you learn anything from a presentation? I want to present this question like a paradox. Because obviously, the answer should be yes. After all, the AAPT, in their incredible wisdom, have given me an hour to present to you. So hopefully, this is going to be worth something, right? Hopefully, you can learn something from a presentation. And if you think about it, our whole culture is built on presentations, on watching TV news presentations, on watching films, on attending press conferences. And you see what we do at conferences. We, talk to each other in venues like this one. So what is the other side of this? Well, the other side is the way that presentations actually really seem to be rather ineffective. Like how we kind of toss out lecturing as, something that doesn't seem to be particularly well suited for educating students in physics. One way to assess the effectiveness of a presentation is to go out on the street, as I often do, and ask people questions and see what they know about the world around them. For example, I could ask them about climate change, as I did here. Let's see how well these presentations on climate change are working.
What's happening around the world, the level of carbon dioxide in the atmosphere? Do you know?
No, I really don't know.
You know about carbon dioxide, though?
Yeah. Is it like increasing or? Yeah.
It's increasing globally, as far as we can tell. And why would that be? Why would the amount of CO2 be going up? You can take a moment, think about it. Why is the amount of CO2 in the world going up? Do you know? But you knew that it was going up.
Yeah. I don't know.
But why would it be going up?
Okay, so presentations. I'm not sure. I mean, I'm sure she's seen a presentation about climate change in some form or other, but doesn't seem to be working. And this is not a rare one-off. I only interviewed, I don't know, maybe 10 people about this subject. Here's another one from the same day. He starts out a little better. See if you can spot the point where he goes wrong.
So what's happening to the level of carbon dioxide in the atmosphere right now?
Well, I guess we've got this whole climate change, and and I guess people believe that obviously carbon dioxide is a it impacts on climate change. So carbon dioxide, everything emits carbon dioxide. Trees, human beings. I guess animals.
So
and
the trees are contributing to the...
Oh, definitely, but it's definitely. So so trees are, I guess, the one of the original primary sources of emitters of CO2.
Okay. I guess as a core of why I do what I do is because I feel like if we knew the truth, if we were more truth-seeking in our own lives, we would act differently. And we would be happier and we would make better decisions. That's at the core of the reason for everything I do. And when I go out and ask these sorts of questions, it's easy to become dismayed and say the whole presentation system, the whole way that we do this is just not working. But I wanted to dig a little deeper because I also love the craft of filmmaking. And I wanted to know for my PhD, how do you make a film that can actually educate people about physics? And I mean, maybe that's not possible, but hopefully you'll be able to find out by doing the experiment. So this is a little summary of one of my experiments, where I took all of the first-year physics students coming into the University of Sydney, and I got them to go online in their own time and take a multiple-choice quiz. There's 26 questions. They were drawn from the Force Concept Inventory and the FMCE. But I'll give you a sample question here. Here's roughly what the questions were like. Let's say there was a basketball player and he's shooting the ball from the free throw line. Once the ball leaves his hand, the net force on the ball is either A, upwards and constant, B, upwards and decreasing, C, downwards and constant, D, downwards and decreasing, or E, tangent to the path of the ball. Okay, pretty straightforward, standard physics question, just checking, do they have a Newtonian sense of the world? Okay, so after each one of these questions, the student would rate the confidence in their answer. My PhD supervisor is here in the audience, and she will note that is not the exact Likert scale that I used, but you get the idea. You get the idea. We were asking them how confident they were that their answer was correct. I mean, my thinking, I thought this data might be useful, so we'll have a look. After doing this pre-test, the students would watch an online video. And this was back in the days, actually, when I started my PhD, YouTube didn't exist yet. That gives you a sense of, maybe lucky timing, that I was really interested in filmmaking at a time right on the cusp of where video became widely available to the world. So the student would be assigned to watch a video, and now what they didn't know was that they actually were randomly assigned to one of several different treatments. This was not something that was known to them. Each one was about 10 minutes, and it was about Newton's first and second laws. And then after watching the video, they would get returned to do the same test again. But before they did the test, it would say something like, hey, you just watched a video about this. Maybe it changed your mind about some of those questions. Think about it as you answer them again. So the same 26-question post-test. And I separately interviewed a bunch of students who had watched the different videos and talked to them about what they liked, what they didn't like. So this is how things turned out. On the pre-test, you'll notice that at the University of Sydney, we actually split our students into 3 streams called fundamentals, regular, and advanced. The fundamentals students have not taken physics at the grade 10 or 11 level. The regular students have, they've done okay, and the advanced students took grade 11 and 12 physics, and they did very well. And as you can see, you know, the results come out, I guess, like you'd expect. The advanced students are doing okay, but the others are not doing great. The regular students, for example, are getting 13 out of 26, but that shouldn't be terribly surprising for those of you who know the results of the FCI, the FMCE. I mean, a lot of conceptual learning doesn't always happen in traditional courses. And then down at the fundamentals, you know, they're scoring around random chance levels, because this is, after all, a multiple choice test. Okay, it's out of 26. Okay, so. Now, what did their confidence scores look like? How confident were they that their answers were correct on the pretest? That's how confident they were. Now, if you want, you could describe, I mean, I think the advanced students, they're pretty good. They're pretty well marked. But the regular students and the fundamental students, they're on the confident side of neutral, which is a concern, you know, when the scores are random chance. This should be cluing us into something, that something is not quite right. Okay, so one of the videos that the students saw, I call the exposition. And we wrote this script by looking at textbooks and basically trying to make the clearest, most concise explanation of Newton's first and second laws that was possible. So we'd tell them, you know, what Newton's 1 and 2 are, and then we'd do a real-world example. There's a guy juggling balls, and we would say, you know, while a ball is in the air, there's only one force acting on the ball throughout its flight. It's the force of gravity. It's constant, and it's downwards. And we would animate the ball flying through the air with one arrow on it, pointing down the whole time, and we would describe the ball's motion. As it goes up, it is slowing down, that is accelerating in the downward direction, and then it reaches its highest point, and then it speeds up back in the downward direction. The whole time, there's only one force acting, it's accelerating downwards. Nice and clear, right? Animations, graphs. We did everything that we thought a good instructional designer would do. We followed multimedia principles, and you know, we did our best for the students. And here is how the students responded. This is the gain in confidence. Now here I'm looking only at the fundamental students because they had the most to learn, so let's focus on them. This was their confidence on the pretest, the correctness of their answers. This was their confidence on the post-test. It's not bad. Now their confidence has risen to the same level as the regulars. So, it's not bad, not bad. We've gone somewhere. In interviews, I asked them, you know, what did you think about the video? Did you like it? You didn't like it? Here's something, here's a little snippet out of those interviews. It was actually a focus group. One student said, having things like the car just sitting on the angle, I think they mean the ramp, with arrows pointing in each of the directions and the size of the arrows changing, showing how the force was affecting it, made it a lot more visual and easier to understand. Another student chimed in and said, I thought it was simple to understand. Another student said, yeah, definitely, very simple explanations. So it makes physics look really simple, which I know is not true. And it was also very clear and concise, to the point, doesn't go around in circles really. Okay, so basically, I feel like we achieved our objective and we made a nice, concise, you know, lecture-style summary with all the multimedia bells and whistles that we could put in a video. Okay, so they liked it so much, I thought I would count up these keywords from the focus group. 7 times they said it was simple, 7 times clear, 4 times concise, 3 times easy to understand. Never did they say the word confused or hard to understand. So, everything's pointing in the positive direction. Let's see how well their scores improved. There are their scores on the pretest, around a 5 or a 6 for this particular group. And their scores on the post-test, they improved by 0.3. 0.3 of 1 mark. Think about what that means for a minute. I mean, you might say to me, Derek, Did the students really do the post-test? I mean, did they just go through and answer the same thing exactly again? So, trying not to fool myself, I went back and looked at the data. Did students change their answers from the pre-test to the post-test? The frightening answer? Yes, they did. But somehow, they managed to not get more right after. Yeah, it's a little baffling. I mean, you think about the logical conclusion of this study, which is that a nice, clear, expository summary is not only ineffective, it's detrimental. Because now they're more confident that they've got it. And you might well at this point throw up your hands and say, presentations don't work. You can't learn anything from a presentation. But I'm not willing to give up that easily. So, question is, what went wrong? As I say, when it comes to presentations, some people will just say, okay, it's a passive environment. They're passively receiving information. They're not being active constructors of their own understanding. Okay, well, I mean, we can say that, but why and how do we fix that? For me, a key to physics education that makes it different from a lot of other types of education are the alternative conceptions, or naive conceptions, or misconceptions, which have of course been in the literature for decades. But what I saw was a particular cycle. So at the top of our cycle we have misconceptions cause misperception. That is, you can't even see what's presented to you if you have a particular misconception. The follow-up is that misperception means you don't pay that much attention. So because you think you know it already, you don't pay that much attention. And then what happens? You get more confident because you think you are watching something that confirms what you already believe. You get more confident, and that reinforces those misconceptions. So this is kind of a vicious cycle. And I have evidence for each one of these from the interviews. For example, misconceptions cause misperception. I was really curious, because how did they get the basketball question wrong in the post-test? I mean, we had almost directly addressed that question. And I asked the student, what did the video say were the forces on the ball in the video? And the student said, gravity is the same on the way down as it was on the way up, except for there was the other force that was pushing the ball up. So that force is steadily decreased until it's reached its point of stoppage or whatever at the origin, and then it comes down with the constant force of gravity. I had sat in that room and watched the same video with that student, but the student saw a different thing than I saw, and objectively a different thing to what was in the video. I mean, you hear about misremembering, but when you see it, and it's like, this question was like 5 minutes after watching the video, and I was giving them pizza to entice them to be, attentive. This was horrifying, right? It's a clear effect that if someone has this alternative conception, you can present things as clearly as you like, but they are going to misperceive what you're doing. Now, another, I think, great example of misperception is to be found in just our perception of our world, our reality. So let's have a look at this challenge to our perceptual apparatus. How the world looks to people who are not physicists.
Got you guys here. So what I want to do is I want to drop the ball. I want you guys to watch it and then tell me how the ball moved.
Okay.
Is that fair enough?
Okay. So you want us to watch it till it hits the ground?
Watch it till it hits the ground,
Okay.
and then afterwards you're going to tell me how it
Yeah.
moved. Okay, 3,
Ready?
2, 1. I'll do it just one more. 3, 2, 1.
I slowed it down for you guys.
Could you tell me about the motion of the ball? What was it doing as it went down?
It's fast. I don't know, it just seemed like it just dropped. Like it wasn't even moving. You just seen the ball drop to the floor and that was it.
You didn't see it like here, you just saw it from there to there.
Yeah.
Would you say its speed was constant, or do you think its speed was changing
Constant. Yeah, it was the same. Yeah.
the whole way down?
Yeah.
No acceleration. There's
no doubt in their minds that a falling object does not speed up. That is what they saw. So, I mean, we have a lot of these cases where we want to say, you know, seeing is believing, and students must experience the phenomenon in order for them to really grasp it. But here, experiencing the phenomena and being told to focus on, you know, a particular thing doesn't help either. Because of, I guess, the smoothness of our vision, for one thing. Our vision's very, very smooth, and that kind of hides what's going on. Maybe if you got them to follow it with some sort of camera or something, they would realize they have to. But even then, I don't know. So my point is, misperceptions are all over the place. And misconceptions really contribute to them. And once people misperceive, it becomes much harder for them to pay attention, and to pay attention to the relevant things. So when I say misperception limits attention, one of the fundamental students said to me, the video wasn't that hard to pay attention to, I think, because I already knew what she was talking about. So I was listening, but I wasn't really paying utmost attention. This is one of those students who scored 6 out of 26, right? But the words sounded familiar. It seemed clear. The person who was explaining it did not seem to have any difficulty. You know, there's a line at the start of Paul Hewitt's conceptual physics book, where he says that, you know, to a physicist, the equation F equals ma, you know, is so rich with meaning. You know, all of us look at that equation and, you know, feel it in our guts and know about all those relationships, and it's an old friend. But to a student, he says, it is like psi equals phi alpha or something. It is just sort of meaningless symbols on a page. It is gobbledygook. And I think that's certainly true, and it's pretty true for students who come new to physics and they haven't seen anything ever before. But then I would argue it actually gets worse. Because rather than remaining gobbledygook, it becomes something that looks like a friend. It looks like, you know, push equals heavy times speed, right? I mean, that's kind of how it looks if you don't have really strong, clear conceptions for things like acceleration. And I guarantee you, you know, most of your students, I don't know what level they are, but the concept of acceleration is like, you know, it's not clear for a long time. It's one of those real challenges. But the problem is it feels clear. And this is the worst part. It's almost like speaking to someone who uses all the same words as you, but has slightly different definitions for each word, or very different definitions for each word. That's going to be a very difficult conversation to figure out what is going on, right? That is physics, kind of, to a lot of students. Okay. So, I've talked a lot about the problem, but what do we do to solve this? I think that there's this spectrum that we talk about a lot, which is a really nice concept. Oh, this one. Learning is an effortful and mindful process, and students should be encouraged to construct their own knowledge and skills through active processing rather than being passive listeners. I'm sure we've all seen a paragraph like this in our day, a sentence like this in our day. And I think it's important, it's instructive, but what I'm concerned about is that we have always assumed that a listener is passive. And my question is, can we make them active? And how do you make them active? Because that has got to be the key to making a presentation work. Because if you are simply passive listeners in this room, then, well, nothing I say is going to work. There are these spectra from, you know, passive to active. That's the standard one I think most of us use. But I think there's some overlapping terminology. I would argue that, you know, disengaged and engaged is also a similar way of saying the same thing. Or zoned out or focused, different ways of saying the same thing. There's also terminology that comes more from psychology, like mental effort. Is it low or is it high? Or cognitive load, again, from low to high. To me, all of these concepts seem to sort of say the same thing. Are your students thinking about the things that you want them to think about? And are they thinking hard about those things? And the key to making listeners active has got to be to use some strategy that pushes them to the right on any of these spectra. But there's a warning, right? Because another part of this spectrum is from being underwhelmed to being overwhelmed. And really what you want the students to be is whelmed. Yes. Can you be whelmed? Think you can in Europe, right? Okay, so I say this not just facetiously, but I'll come back to this idea of overwhelming. But that's important too. But I think the key in a presentation, or the key in a video, in multimedia, or even in text, is often to shift the viewer, shift the learner to the right. So the question is, how do we do that? Now, there's been a lot of evidence that dialogue is effective. For example, Eric Mazur's peer instruction, of course, incredibly effective. Now, a question that I would like to ask, and the question I did ask, was, when a student asks a question in Eric Mazur's lecture hall, is that question only beneficial to the student who asks it? The obvious answer to me, no. Everyone gets to hear that question. Many other students are thinking that question. So many other students get the answer without even having to, stick their neck out. So what if we made a video in which there is a student and a tutor, and the student says the things that I know the students watching it are thinking. And then we animate that, we show it as clearly as we can, and then the tutor says, well, I don't know if that works, and then through this social interaction, modeled on screen, they get to the right answer together. So I made a different video, which I call the dialogue, in which this student and tutor talk, and there was all the same correct information and graphs and animations and diagrams, etc. But there were also incorrect graphs and animations and diagrams. And we didn't warn the students who were watching the video, hey, there's going to be wrong stuff in here, be careful. We just let them deal with the social negotiation of meaning that was presented for them in this video. So for example, the student would say, while the ball is in the air, there's a force upwards from the hand and drives it upwards against gravity. And we'd have these two different arrows on the ball like this, right? And then the ball goes up, and he's saying, as the ball goes up, that force gradually dies away, and then at the top, gravity wins and the ball falls down. We've all heard that story too, I'm sure. So, and then the tutor says, I don't know. And anyway, eventually they get around to the right answer. But the point is, it's a longer video because you're putting incorrect stuff in there as well as correct stuff. And students really have to figure out, who's right and what's really happening. So we tested out the dialogue. And you remember those keywords from the exposition? That's what the exposition kids said. When I interviewed the kids who saw the dialogue, this is what they said. Nobody said it was simple, clear, concise, or easy to understand. In fact, most often they said it was confusing or hard to understand. Okay. Some confusion is good. Okay. Here are the results. So we got pre-test, post-test for the exposition on the left. We have pre-test for the dialogue group on the right. All of those results are not significantly different from each other. And then the post-test for the dialogue students nearly doubles their scores from about 6 to 11. Okay, so they're not Newtonian thinkers. I'm not going to say, hey, give your students this 10-minute video, Newton, done. We obviously know that's ridiculous. But the point is, they learned something. They gained something from that presentation. And in fact, you can see it in the interviews. This student said, I like that the guy was just as confused as I was to begin with. The fact that he was confused kind of helped the whole explanation process in me. Oh, this points to her head to understand. Another student said, saying all the common misconceptions, that was really helpful, so you know what it is, but you also know what it's not. So you can know that if you end up with that, you're like, no, can't be that. So that helped a lot. I said, did you have anything like that? And the student said, yeah, the juggling ball one. The misconception is there's a force and that it's slowly decreasing until it reaches the top and then it disappears or whatever. That was the misconception, I think. Now I gotta say, this student still answered the question about the ball wrong. But they had started down a path. They had started down a path to figuring out what was going on. They had footholds in this terrain. Sometimes when I give these talks to teachers, they come to me at the end of the talk and they say, okay, Derek, I've got it. Got to get in there and blow up those misconceptions. And I have to stop them and say, whoa, 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 whoa. That's not the message. I mean, the honest truth is you'll never blow up the misconceptions. Because they're so deeply ingrained, they're so well held, that if you can rely on anything in that kid's brain, it's the misconception. You can rely on that, it's going to come up time and time again. So if instead of trying to blow it up, you attempt to leverage it, to sort of build a structure around it that says, this is the way the world kind of seems sometimes because of X, let's say friction, or because of Y, let's say momentum or something. We can build onto it, which I think is so much more constructive than this idea we have to blow it up. You can count on that misconception being triggered. They will cue it every time. So I guess the point is that we need to be building on the misconceptions, not attempting to eradicate them, but using them to build structures that work. Now, this, I think, is perhaps the most exciting result of the research, which was after watching the video, and remember, all students are watching these videos online, from home, in their own time. This is before the era of YouTube. And after the video played, a little question popped up and it said, how much mental effort did you expend while watching that video? You can measure mental effort, by the way, using skin conductivity measurements, using blood pressure, using heart rate, pupil dilation, and what has been found is that remarkably self-reports correlate with all of those measures. You can just ask them. Did you really, invest mental energy in watching that thing? Students who saw the exposition rated roughly a 5, which on the Likert scale was neither low nor high mental effort. Students who saw the dialogue reported a 6, rather high mental effort on average. The reason I think this is important is because it means what is presented changes the way that people view. And that can have a big impact on learning. So not all presentations are created equal. Some can inspire learning. But it does seem very important, particularly in physics, that alternative conceptions are explicitly addressed. And that is particularly true for novice learners, for people who are new to the program. So when I think about like the flipped classroom, for example, I know that's very popular. One of those things I think about is, what videos are students watching from home? Are they watching clear expository summaries that have no mention of alternative conceptions? In which case they may come to you more confident in the incorrect stuff than if they watch nothing at all. Something to keep in mind for the flipped classroom. Now, when I think about this, and I think about investing higher mental effort, I think about other circumstances in which this pops up. I have now kind of taken this on as one of those things that I do in the YouTube channel. I talk to people and I create dialogues out of these random conversations with people on the street to hopefully, educate the people who are watching it who have the same types of cognitive biases. And this is perhaps the video I'm most proud of, and the video that maybe is most useful to all of you here. It's a video which is ostensibly about a number game, but is really kind of about the scientific method. So, let's check it out.
I'm going to give you guys 3 numbers, a 3-number sequence, and I have a rule in mind that these 3 numbers obey. And I want you to try to figure out what that rule is. But the way that you can get information is by proposing your own set of 3 numbers to which I will say, yes, that follows my rule, or no, it doesn't follow my rule, and then you can propose what you think the rule is. Is that fair?
Yeah.
Yeah, okay, so here are the 3 numbers. 2, 4, 8.
2, 4, 8.
You don't need to continue the sequence. You can propose a totally different sequence, whatever you want to propose, and I will simply say yes or no. That follows my rule.
2, 4, 8. 16, 32.
16, 32, and
64.
Those also follow my rule.
Okay.
What's the rule? What do you think?
multiply by 2.
That is not my rule.
What?
That's not my rule. But you're allowed, if you want, propose 3 other numbers.
3, 6, 12.
3, 6, 12.
3, 6, 12 follows my rule.
10, 20, 40.
10, 20, 40.
That follows the rule.
Yeah, I'm still multiplying by 2.
I know. I know what you're doing. And yes, it follows my rule, but no, it's not my rule.
5, 10,
10 and 20.
Follows my rule.
100,
200. 400.
Follows my rule.
500, 1,000, 2,000.
Follows my rule.
Want me to keep going?
But do I just keep going? You're going to tell me your rule?
Am I doing it the wrong way? Am I approaching this the wrong way?
You're totally fine,
Okay.
but you're approaching it the way most people approach it. Like, think strategically about this. You want information.
Yeah.
I have information. The point of the 3 numbers, right, is to allow you to figure out what the rule is.
Okay.
Okay, I'm going to give you the numbers that I don't think fits the sequence and then see what you say. So I'll say 2, 4, 7.
Fits my rule.
So whatever I propose is right?
So is your rule like you can propose any number?
So the rule is anything we say is yes.
No.
Damn it.
But you are on the right track now. Hit me with 3 numbers.
3, 6, 9.
Follows my rule.
Oh, that didn't follow my rule.
This is good, right?
5, 10, 15.
That follows my rule.
What? Oh. Really?
Yeah.
I don't believe this.
1, 2, 3.
1, 2, 3.
Follows the rule.
What about 7, 8, 9?
Follows. Yes, that follows the rule.
8, 16, 39.
Fits the rule.
Excellent.
But we're no closer to the rule. I want you to get to the rule.
How about 1, 7, 13?
Follows the rule.
What?
11, 12, 13.
How does this
Follows
make
the rule.
sense?
10,
I don't
9,
know how
8.
to do this.
Does not follow the rule.
10, 9, 8 does not.
Oh, so is it all in ascending order?
Booyah.
Okay.
Up top. Yes, first
that
ones
what
to
it
get it. You guys nailed it. That's the rule. That's the rule. Numbers in increasing order. Numbers in ascending order.
Oh, so much.
1, 2, 3, 4, 5, 6, 10, 15, 25. Doesn't matter. Any numbers in ascending order. I was inspired to make this video by the book The Black Swan by Nassim Taleb. Now, the black swan is a metaphor for the unknown and the unexpected. I mean, in the old world, the theory was that all swans were white. So each instance of a white swan would make you think, yeah, that theory's pretty good. But the point is, you can never prove a theory true. And in fact, when people found Australia, they realized that there were black swans. What was interesting for me was that everyone I spoke to came up with a rule very early on and then only proposed numbers that fit with that rule they were thinking. I was looking for you guys to propose a set of numbers that didn't follow your rule and didn't follow my rule. I was looking for you guys not to try to confirm what you believe. You're always asking something where you expect the answer to be yes, right? Like you're trying to get at it.
Yeah.
But instead you want to get the no.
You want to get the no because that's much more informational for you than the yes. Like if everything's
No, that
giving a
is
yes.
true. That is really true once you say that.
That is what's so important about the scientific method. We set out to disprove our theories. And it's when we can't disprove them that we say, this must be getting at something really true about our reality. So I think we should do that in all aspects of our lives. If you think that something is true, you should try as hard as you can to disprove it. Only then can you really get at the truth and not fool yourself.
All right, so I guess that shows the evolution from, working on this as a thesis project to working on this as a project to try to inform the general public about cognitive biases, misconceptions, and physics more generally. And the key to me is that there are things that we can do to change the way people watch, to move them further along that spectrum towards active, towards engaged, and hopefully whelmed. You know this bat and ball question? Bat and a ball together is $1.10. Okay. If you give this question, along with a few other questions, there's a standard inventory. It's about 4 or 5 questions. You can give it out, and it's been done in universities around the US at the very least. And what you find is that typically, even at elite colleges like Harvard, MIT, Stanford, etc., 90% of students will get at least one of these questions wrong. They're simple questions, bat and ball questions. Now, take that text, take the questions, and reduce the font. Make it light gray. Maybe something really ugly, like Comic Sans. I don't know. Just do what you can to obscure the questions. This has been done. Hand it back out to those students. Randomly mix up those 2 tests. You'll find that the error rate drops from 90% to about 35%. Making questions harder to read shifts people towards the active side of the spectrum. No longer will they just endorse their gut feeling. Because they're having such a struggle to figure out the question in the first place, they'll actually think more carefully about it and answer it more correctly. Maybe this is something you could experiment with your physics tests. Print them in really illegible font, make it really difficult to read, and see if they do better. I only mean this half facetiously. Like, there's a good chance it shifts them along that active spectrum. It shifts them towards the right. There is a question you have to answer, which is, how much are you willing to put up with? Or what types of shifts to the right do you really want? Because there's a lot of things you can do to shift to the right. As we've seen, dialogues involving misconceptions appear to do it. Poorly written tests appear to do it. Let me show you a little advertising campaign. This is an advertising campaign out of Australia. So I know there's some Aussies in the audience, but everyone else should have no idea what this campaign is all about. This appeared on billboards around Sydney. The power of un. Who here knows what this is advertising? Hands up if you know what this is advertising. Australians? The Australians don't know either. Are you kidding me? This advertising campaign did not work on you. Because it worked on me. Okay, so here's how they did it. What is the standard principle of marketing? Tell people what you're selling, why yours is better than the other guy, and tell them where to get it or who you are, right? These are the keys of marketing. I'm selling this, it's better because of X, and I am Derek, come buy it at my store, right? What does this do? There's no branding, there's no, our product will make you smarter, faster, it's the power of, it's barely a word, I want you to go and look at the advertising you see around you, and I guarantee you will notice the same thing I have noticed. That in the last 20 years, we have shifted from make the message easy to get to make the message hard to get. Why? Because the marketers want to shift you on that spectrum from passive to active. There's so much noise in your world that you block it all out. Just like those students block out your clear expository summaries, for those of you who still offer clear expository summaries. For the simple text, it's too easy to ignore, to invest neither high nor low mental effort, to just let it wash over you like a commercial on, TV. But if it's weird, if it makes no sense, if it's barely a word, that will grab your attention. And now they've got you. Now they're pushing you towards the active. I mean, look, we've figured it out in education. They've figured it out in marketing. I mean, when they've got it, you know it's something good, right? Because they're making dollars off this. We are just making informed citizens, which, super important too, but, they're making money. So, okay, what the heck was this campaign about? They followed it up. They followed up these massive billboards. They spent millions of dollars. It was a big, big company in Australia that did this. Okay? They followed this up, massive billboards, with stuff like this. Okay. Unexplained. With there is no stress. Just unstress. No hassle. Just unhassle. With you can undo what you did. You can undrive through the car wash with the window down. Or un-break dance in front of your teenage son and his mates. Or unflood the downstairs laundry that now doubles as the pool room. Makes life relaxing and unreal. Your life. Be happy and live for now. Don't worry. Unworry. Have the Aussies figured out what this is an ad for yet? Say it. It's an ad for insurance. It's an insurance company ad. How boring are insurance company ads, right? Not anymore. They got that if they just presented to you, hey, we can save you $10 in your car insurance. Like, yeah, everyone says that. What about this? This is innovative. There's art here. As well, I think there is art in teaching. Let me make a little detour, because, as I say, there's more than one way to skin a cat. I didn't say that, but then I did now. Okay, so there's more than one way. There's more than one way to push people on the spectrum. For example, that marketing is great. What does that marketing lack? It lacks information. If you give your students less information, they will be more active. Why? Because you're not giving them anything. So they have to be more active. Walk into class, give them a problem set. They will have to be active. Otherwise, what are they going to do? You can whip them. But my point is, you have to think about what works, what you like. There's many ways to push people towards being active. Which strategy are you comfortable with? Which one do you like, do you think will be effective? Which one is artful? Now, as a filmmaker, this is one particular strategy that I tried, which I think is artful. And this actually came out of a meeting at an AAPT meeting. So I thought, again, good to share. I had a meeting with Dave Jackson and Bob Teese in Portland a couple years ago, summer meeting. Again, good choice of location. And they talked to me about this problem. And I ended up visiting with Priscilla Laws and Bob Teese and Ken Jackson, of course, and Dave Jackson, in Rochester, and we ended up making this video. So check it out. This is another way of pushing people to be active. All right, here is the setup. I have a rifle mounted vertically, and we're going to shoot a bullet into this block, right into the middle of it. And so obviously the block is going to go flying into the air. But we're going to do this again, and instead of firing the bullet right into the middle of the block, we're going to shoot it off to one side. And I want you to make a prediction. Will that spinning block, when we hit it to one side, will it go the same height as this first block? Will it go not as high, or will it go higher?
And so the total energy of the system
basically has to stay constant, and the kinetic plus potential, which would be the height it goes to, will have to be constant. So if it's spinning and has kinetic energy, it can't go as high. That's my prediction.
So my prediction is it'll go up, not as high, but it'll spin more if it's hit to the side. Am I wrong?
I want you to think, which do you think is the most reasonable, and then click one of the annotations above. All right, are you ready? Make your prediction in 3, 2, 1. Do you guys know who those two guys were in the video? It's Minute Physics and Destin, who makes a channel called Smarter Every Day. They're both prominent YouTubers and friends of mine, at least until this video. No, they took this good-heartedly. So something that's interesting about YouTube is you can actually click on the screen on the video to go to another video, to follow a link. So the way I posted this video was, you can't see what happens until you click one of those links. You got to make a prediction or you can't see the answer. That's the way this went down. And what did the results look like? Because you can track those link clicks. The results looked like this. Roughly 3 times as many people clicked that it would go lower compared to either of same height or higher. And if you want to know the absolute numbers of people that were clicking, we're talking about n greater than 600,000. This is a data set the likes of which I could not have imagined when I was doing my undergraduate. Okay? Forcing people to make a prediction. Again, shifting them to be active. So, what actually happens in the video? Well, I'll show it to you. We've moved this block, so now the gun is actually firing into the right side of the block. So presumably, one imagines that the block will spin anti-clockwise.
3, 2, 1.
Now check out the high-speed footage. You can clearly see that both blocks go to the exact same height, even though one is rotating. And that's a bit strange because they were both hit by the same type of bullet from the same rifle, so presumably it had the same kinetic energy. And they both go the same height, so they both have the same gravitational potential energy, but one is rotating. And so it has that additional rotational energy. So one block has more energy than the other block.
I don't know if I buy that, Dr. Muller.
Yeah, talk to me.
Yeah, I mean, so you're telling me you just created energy?
Not necessarily created energy.
Okay.
So what are you thinking there?
I am potentially surprised.
Is it the same height? Speed footage.
Obviously I'm wrong.
They went up to the same height, which is incredibly confusing to me.
Why is that confusing?
Because where's that extra energy coming from?
But the fact is that one block clearly does have more energy. You think about them both at the top. One's spinning, one's not. They basically have identical gravitational energy, but one does have additional rotational energy. How is that possible and why is it happening?
No, explain it to me.
I don't want to give you the answer right away.
I love it when you say that. I don't want to give you the answer. That means you don't know.
So if you can make me a video response, I would love that. Or if you just want to post your idea in the comments below, that'd be great. And I will reveal the correct answer next week. So subscribe to the channel if you haven't already, and you'll find out in a week's time.
After I have time to pour over the footage and consult a very smart man in the subject. That's what you didn't say.
Okay, so again, rather than explain this to people, we left them hanging. And you saw I made that request there for a video response to see if anyone wanted to, submit their ideas to me. And this is just a fraction of the responses.
If you imagine a bullet traveling through the center of the block, then after the collision, the bullet has moved into velocity of the block.
So that's perhaps one of my proudest moments as a YouTube creator. There is such opportunity right now to leverage technology to get people involved and push them in the active direction. I think that there are so many ways to do it, and we just have to go and explore and experiment to find those ways. The one last thing I want to talk about is this misconception. Energy being bound in molecules. Because I want to branch beyond the virtual world and I want to invade people's physical space. A little bit. Because I think we can do something about this. This is actually a slide from a current course being taught at a major US university. And it says, molecules in living cells have potential energy to do work because of the arrangement, orientation of their atoms in space. Fine. We call this chemical bond energy. Okay. The energy of cells is stored in the covalent bonds of their molecules. No. I take issue with this. Because if energy is stored in bonds, why don't they just break open and release their energy? I mean, how does that make any sense? The way that I think bonding makes sense is if you bring two things close together, just as in, gravitational attraction, two things, you bring them close together and they bond. Because they're in a lower energy state here than they were separately. They've in fact lost energy. So what should we say about bonds? Well, to break a bond, that takes energy. You got to put work in. You could form, another bond that perhaps releases more energy, but takes energy to break bonds, and energy is released when bonds form. So I decided that rather than the old ball and stick model, what I wanted to do was make some things with magnetic attraction. So basically, not only can you have a space-filling model that is more like what the molecules really look like, gives you a better idea of overlapping electron orbitals, and gives you a nice rotation of your single bonds. Also really easy to break apart, right? But most importantly, allows you to feel that these atoms like each other, right? That they attract. And that when they bond, they release energy which you can hear, the sound energy. And if you want to break those bonds, then you have to put in work to do that. So I've created this product, which I call Snatoms. And we are currently crowdfunding it on Indiegogo. If you are curious about them, you want to learn more, or you want to talk to me about some sort of bigger distribution deal, then please see me later. But my goal is to really try to further this idea of pushing people up the active end of the spectrum in whatever means I can. So to close out, I think you can learn from a presentation. In fact, I think you learned from this presentation. I hope you did. But there's some particular criteria, like a presentation has to contain limited novel information. I think this rule is broken by almost every physics lecture, and that may be why they're typically ineffective. It must explicitly address misconceptions. This can be done in dialogue in the class as it's done with peer instruction, or it can be done in a video. I mean, there's a lot of creative ways to do this. And when you address those misconceptions and when minds are changing, that will necessarily cause confusion. And this confusion is good. But I called the talk, Why Some Confusion is Good. Because you can also have confusion without learning, quite clearly. If you leave students really completely on their own, they will be confused and no learning will take place. So I think the goal as a good teacher has to be to find the art of how much to tell, how much to show, and how much to leave to the student. Because, we have to push them up that active end of the spectrum. And I'm sure there are a great many of innovative ways that you guys have all come up with to do that. So, thank you very much.